Welcome to another RDWorks Learning Lab. Now we're going to start off today by looking at a couple of samples that I did after we closed the last video. You may remember me mentioning when I was busy floundering around chucking lenses together to try and find out things that worked, that I came across something that looked very interesting as far as a short focal length lens was concerned. And it was a couple of gallium arsenide 2-inch lenses placed plano side down. Here is the performance of that lens. Now I compare that with this lens here, which is my current compound lens. Now when I start looking at the two of them, there are big differences. They don't look much different as far as depth is concerned. Now when we start looking at those last few, you'll notice they've got a sort of a bulbous shape at the bottom, but they've got a straight piece at the top, parallel section before they go into a bulbous section. Let's compare that with my short focus lens. And what you'll see with the short focus lens, there is no straight section. It immediately starts going into a bulbous blob below the focal point. Now that's exactly what I would expect if I've got all the energy focused at the focal point, and I do mean all the energy. The big difference between a short focal length lens and a normal lens, I think that on the right hand side is a 2-inch lens, but compare that to my compound lens. Big difference in the shape of the burn. So this test in acrylic that we're using is telling us a great deal about the way in which the energy within the beam is actually causing evaporation within the acrylic. Now it would be fantastic if wood was transparent as well, but it's not. So my big problem is, how can I see what's going on in wood so that I can compare wood with acrylic to check the performance difference of the lens in these two different materials? Well, I've come up with an idea which I think is going to present me with some sort of answer, and let me show you what I've done. There's the basic principle of it. It's just a nest. Now what I've also done is cut some small pieces of plywood like this, and here I've got 5 pieces of 3.2mm plywood. That is, give or take a little bit, 16mm. So what I can do is to slide these into the end here, and halfway along this at the bottom here I've got a ramp which has got a springy bit in it. I purposely made it so that when I push it in, it runs over the ramp and it won't go under these two stops at the end here. What I have to do is to push it down against the springiness and slide it under those two little clamp bars. So now I've got a stack that's 16mm thick, tightly clamped together to make it look like one piece of wood 16mm thick. We run exactly the same test that I ran on acrylic. And now when I take that out of there, so there's my dot pattern on the top, and if I turn it over, what I shall find is just there by my fingernail you probably can see 2 little black dots where the 70 and 75 millisecond pulses have just made it through, all the way through. So at various sections through here I should be able to work out how far my beam has penetrated. Now I should be able to get an approximate comparison between this and acrylic. Okay, it's crude, I don't get as much data, but I get enough points to indicate the difference between acrylic and wood when we're using these same lenses. So I don't muddle these sections up. I put a 4mm hole through the middle so that I can clamp that stack together. So by putting a diagonal line across here, I'll make sure I keep my layers in the right order. I'm going to take the best lens from each focal length and perform the wood test on it, and then we will see what the comparative results are. People have seen me do this before, but In this number 3 nozzle, which is a cutting nozzle, there is a recess in the end here which is specifically designed to take 1.5 inch lenses. So I've got a 1.5 inch meniscus lens, which is my test lens, and I'm going to pop it into there with an O-ring on top. And then I could wind this on, but of course the shoulder in there is so far down that it's not going to clamp. And the way that we deal with that is we just take a standard clamp ring and we just wind it in a few threads like that, maybe 6mm. And now when we pop that on top and we do this, we wind the lens tube on, we should feel it biting on the O-ring before it hits the bottom of that shoulder there. And now it's clamped. I play with so many lenses in so many orientations, and I've only got a limited number of lens tubes that I really never know what the focal point of any of these lenses are. So when I want to do test work like this, I have to do it with my lens test. Now I know that this is going to be pretty short, so I'm going to start off with dropping the nozzle to 2mm. Now I'll just run my focus test. Now what I'm going to be looking for is the thinnest possible line. Bearing in mind I started off with a 2mm gap. That's 2, that's 3, that's 4, which is obviously thin. 5 is going thick again, and 6, 7, 8, 9. So 4mm is the correct focus for this lens. 2, 3, 4. Now I bet these don't come through the other side, because this is a 1.5 inch lens, and I don't think that's going to penetrate through 16mm of plywood. Am I going to be surprised when I turn this over? No, there's no dots on there at all. What about the one underneath? No, there's nothing on there. And the one underneath that? Yes, we've got some dots on there. So it's gone through 9mm. That's it, and then it stopped. It might be different when we turn the lens over. Now that we've turned the lens over to flat side up, we'll just run the same focus test again beside the original one to see what the difference is. And this time 2, 3, 4, 5, 6 is changed by 2mm. So this is an 1.5 inch meniscus with a flat side up. And sure enough, we haven't got anything. The next layer, again nothing, and the layer after that, more. So we've got an even flatter curve on this one. So it would be interesting to plot these out and see how they come out. Now you've seen these graphs before, and what we've got here is, this is acrylic, and this pink line that I've drawn at the top here is the latest wood results. I've already pre-warned you that wood cuts faster than acrylic. It's a different chemical composition, and it has got different cutting properties that allows it to cut faster, generally almost twice as fast as acrylic. Now I don't know whether that makes sense here. Let's just have a look. We get to 8mm in 30, but we're getting to 8mm in around about 75 milliseconds. Well, that's again, that's about a ratio of 2 to 1, twice as fast when cutting wood. And this CVD lens has used what I would class as the right way round, i.e. it's got flat down such that the parallel rays hit the convex surface first and then get refracted and pass out of the bottom flattish or recorrected surface in the case of a meniscus lens. So this is used the right way round. When you use that lens the opposite way round, you get a different set of results. Now apart from anything else, the slope is now quite a lot greater. So it means that if you want to cut thick materials, particularly wood or even acrylic, you still are better to use this lens flat side or meniscus side up. If we say 8mm, it takes what, 20 milliseconds to reach 8mm deep, and about 35 to get to the same depth in acrylic. Not quite 2 to 1, but in that sort of region. So remember that slope there, that's around about 60 degrees. So now we'll drop down to a 2.5 inch gallium arsenide. Now again, use the flat side up, which is the wrong way. Now this is more of a compound curve than a straight line that we saw for the 4-inch lenses. That's more or less 30 degrees, a rapid rise all the way up to 6mm thick material. That's pretty good. And then it starts to level out here, both for acrylic and for wood. But again, if we check what happens at 8mm, a ratio of round about 2 to 1. Obviously that changes down here because it's 1 to 1 down here. But once you get up into these higher regions, 2 to 1 or even better. This is the gallium arsenide the right way, i.e. with the flat down. And again, if we take a look at the average trend here, probably this has got a faster rise time up to 6mm. In other words, you're best to use it the wrong way up if you're only cutting up to 6mm. But if you want to cut above 6mm, then it makes sense to flip the lens over and use it flat side down, because it starts going up pretty quickly. Now this reaches 16mm deep in around about 55 milliseconds, and we compare that to the 4-inch lens, and that reaches 16mm in about 60 milliseconds. So the gallium arsenide overall, used flat side down, looks to be a better bet for average general use, certainly for wood. I'm not so sure about for acrylic, because it drops off quite badly for acrylic. It's quite fascinating, the difference in which the way these lenses perform differently on different materials. That was unexpected, because I was expecting this to be much the same sort of pattern. At 12mm thick, this starts losing it pretty badly. A 2-inch lens looks to be very good for cutting wood, up to 4mm, and then again it starts to drop off very badly. And it follows the same sort of trend as acrylic, which is the sort of pattern that I was expecting. You'll see that the 4-inch, that looks a similar pattern to what I was expecting, just a bit faster. This one, similar pattern, just a bit faster. This one, 4-inch, similar pattern, just a bit faster. This one, a little bit odd. Now we get onto the 1.5 inches, which is a real puzzle to me, because, as I said, every other lens has got roughly a ratio of 2 to 1. This one hasn't. They're almost running 1 to 1, as you can see. And when we take a look at the other option, which is flat up, again, almost 1 to 1. Wood to acrylic. So a 1.5 inch lens is not what you'd call a cutting lens. Right, so we're going to have to try and relate these numbers now, particularly for wood, back to some sort of reality. Now that I've done these results and proved what I've known for a long time, that this is a fantastic lens, I'm going to dedicate this lens tube specifically cutting with a 2.5 inch gallium arsenide lens. Now, to do that, what I've done, I've put my lens in here. I've arranged for a spacer here to make sure the gap between the work and the nozzle here is about 1mm. So I've sorted out the focus, and I like to try and keep the gap as small as possible so that I get maximum air efficiency. With my little 3 psi pump, you'll be amazed at what it can do. We'll take a look at the chart here, and it says for 3mm birch plywood, I'm going to run at about 4 milliseconds per pierce. We've got nothing to judge this against, so I'm making a pretty crude assessment of how I think this chart might be used. The question is, what sort of kerf are we likely to get with a 2.5 inch lens? I think the answer is around about 0.15 millimeters. So that means I'm going to finish up piercing holes roughly 0.15 diameter. If I put holes down that are 1, 2, 3, 4, 5, 6 side by side at 0.15, that gives me 9 millimeters. So I need 2/3 of a hole there, and we've got ourselves 1 millimeter a cut. Now, as I said, this is a crude analogy, but it's a starting point. Every one of these holes, we said, was going to take 0.004 seconds or 4 milliseconds. If each one of those is taking 4 milliseconds, 1, 2, 3, 4, 5, 6 and 2/3, 6.8, say, times 4, that's 27.2 milliseconds per millimetre. And we know that there are 1,000 milliseconds equals 1 second. If we divide that by 27.2, now my two grey cells have not got enough muscle to do that calculation manually. I know that it's going to come out somewhere near, what, 25, 40, less than 40, 35 millimetres a second or something like that. 27.2 equals about 37 millimetres a second. But of course, what we don't know is how accurate this factor is here. So what we really might have to do is to take this number here, 27.2 milliseconds, which is our basic calculation, and modify the formula in this instance, and then test it with other instances to see if there's a common factor. Let's just show you what I mean. If I take 1,000 millimetres a second and divide it by 27.2, okay, I get 37 millimetres a second. But if I multiply that by some factor f equals what we actually get. So I could get 20 millimetres a second, for example, in which case I've got to make that factor 2. On the other hand, I might get 70 millimetres a second, in which case I've got to make that factor 0.5. So there's a fairly simple calculation there that allows us to use this graph to work out what speed we can get for a particular thickness of cut. But what we don't know at the moment is this magic here, F. Well, look, you can tell things are getting serious now. I've got my solid steel table on. We'll put some 10mm spacers underneath the work. And here we've got a piece of 3mm, well actually 3. I'm going to make a possible escape road here for why things don't go right. This is actually 3.2, so my calculations are a little bit adrift. Are we going to be too worried? Well, it depends whether I get egg on my face or not. I've got that gap set to 1mm, which just happens to be the thickness of that ruler. I'll just set the focus. There we go. That's how quick it is to set the focus. I don't think autofocus can do it that quickly. Now we're going to cut a 25mm square. The prediction was 37. As I said, I've got quite a lot of experience with this lens, and typically on this sort of material I would expect it to gobble it up at 35mm a second. So 37 is not really pushing it a lot, I don't think. We'll turn the extraction on and we'll give it the best possible chance. Well, it did that without even thinking about it. So here we go at 40mm a second. Gobbled that up as well, didn't it? Try 45mm a second. 45mm a second didn't fall out, but it's hanging in there by the merest thread. Push it to 50 and see what we get. Now I saw a little bit of smoke coming up on top that time. We take a look at the back. As you can clearly see, it's cut through at 50. I don't know whether you can see that along that bottom there. Along that bottom edge, we've got basically perforation mode, as I call it. It's the same sort of thing that you saw when we were cutting acrylic. Just as it's about to fail, it begins to perforate on the bottom, and that's because basically the stepper motor is allowing the pulses to start, stop, start, stop. So it's going deeper, shallower, deeper, shallower. But on this machine, that error is not very large at all, but it's still there. There's still a stepper motor which is causing that. So look, I've only got to probably gently touch that and it pops out. Now if we look carefully on the edge there, you may well be able to see the serrations on the edge. I mean, the edge is perfectly clean. It's not scorched at all. It's a lovely cut. But we will just test this at 55 as well. Well, I can still see smoke coming out underneath, and it took very little to take that out, and that's 55 millimeters a second. So how do we call this one? As I said, my personal preference would be to call this at around about 45 as a comfortable cutting speed. We'll just go back to that again and test it at 45. Now we'll watch this one from the top so that you can see the smoke being drawn away underneath, out the back at high speed. And look, as you can see, it's already on the edge of falling out. So that's what I would class as a successful cut. So let's go back and see what that means for our equation. At 45 we've got virtually nothing in the way of perforation marks on there at all. We've got a nice smooth cut all the way around, and it's lovely and just honey golden really, or very pale brown, not scorched, no charring. It should be a 25 millimeter square and it's 24.87, and our hole 25.18, and it makes 0.31 millimeters. Divide that by 2 and that equals 0.155 millimeter kerf. So my original choice for 0.15 kerf is spot on. So 37, divide that by 45, that factor is 0.82, say 0.8, let's be round. So I could use this method of assessing speed up to that point there. Now what happens up here starts to get a bit questionable, because first of all I don't have any 8mm material. What have I got? Actually I've got some material. Let me just have a quick look what I've got. Okay, so I've found some more plywood here. It's about 8.8mm thick. It's faced, and I don't know what it is in the middle there, but it might be birch plywood in the middle. We're taking a bit of a punt with this one, but if we use the same sort of parameters that we used before, when we look on this chart we shall find that 8.8 comes out at round about 20 milliseconds per pierce. Okay, so if we use that 20 milliseconds per pierce, we've got the same lens in, so we're expecting a kerf of 0.15. Each one of those is now taking 20 milliseconds, and there's 6.8 of them. So 6.8 times 20, 136 milliseconds per millimeter. So if we take our equation 1000, divide that by 136 times 0.8, the answer comes out at, so that says 9mm a second. Well, the good news is we've got lots of smoke and flames coming out underneath, which means we're travelling far too slowly. It's going to just drop out of there without any problem at all. Look at that. We've gone from 9 till we got to 12mm a second. We're still sending smoke out the bottom, which is good news. Wow, just over 15. We've still got smoke coming out the bottom. Just hanging in by the corners, I think. We'll do another one like that and check what's underneath. think you can see that probably that's a good cut, except just there, look, just missed that corner there. Yeah, that's all that's holding it in, just that little teeny weeny corner just there. It's a much darker cut than we had with the thinner material because we are travelling slower, so we're likely to be scorching a bit more, but we're only scorching, we're not charring, because look, if I do my char test, I can't pull off any carbon on there. It's a nice clean cut. I think we've nearly reached the limit now at 15 millimeters a second, so let's go back and see what that does to the formula. Millimeters a second without an adjustment factor. Well look, we'll double that, so that factor there, instead of 0.8 needs to be 0.5 to get the right answer of 15 millimeters a second. 0.8 was suitable for 3 millimeters. 0.5 seems to be suitable for 9 millimeters. So there is no common factor here. I'm going to have to think about that a little bit. Now, while I was hunting for that piece of that 9mm plywood, I came across something that I thought, should I, shouldn't I, will I, won't I, can I, can't I? Lunacy really, but what I'm going to do is this. Look, I love my 2.5-inch gallium arsenide lens, and here it is. I'm going to extend the graph. We'll take an average, somewhere like that, and we'll extend that graph like that. Now 16, 18, 20, 22, 24, 26. Or 25, somewhere here. Now the reason I'm going to do that, I'll show you in a second. It's because, let's have a look to see what this projects and predicts. 25mm thick material, (94 millisecond). Let's feed those numbers into my equation. We know all this applies the same because I'm going to be using the same lens. So it's still going to be 6.8 pierces per millimetre. 6.8 times, this time we said the pierce time was 94 milliseconds. 94 milliseconds. Okay, so that equals 639 milliseconds per millimetre. So if I divide 1000 by 639, I get 1.6 millimetres per second with no correction factor. Now if I used a 0.5 correction factor, that would take that up to 3.2 millimetres per second. Now you're going to fall off your seat and laugh in a minute, because some people can't even cut this stuff at 3.2 millimetres a second with their machine. I've got 60 watts here, maybe 65 watts coming out of that nozzle. So here we've got a piece of wood that's 26 millimetres thick. And I'm giggling away to myself here because this is not just a piece of wood 26 millimetres thick. I think anybody that's done woodwork would recognise that as oak. That happens to be English oak, which is pretty damned hard. It's not the hardest wood in the world, but it's a hard wood. Remember what I just said, some people can't even cut that stuff with 60 watts on their machine. Mind you, I don't think their tube is 60 watts. It may claim to be, but it's not. So we're going to try and cut with my magic gallium arsenide lens, and let's see what miracles it can perform. I've got a lot of faith in this lens, but I think I might have pushed it one step too far with this demonstration. So what did it say? It projected we might be able to get to 1.6. Now, did God give me the equipment to actually try this at 2mm a second? Ah, what the hell. We just set the focus to 1mm. There we go. So we'll just turn the extraction on. Well, the good news is, look, we've got smoke coming out underneath. And what does that mean? Oh, I've never done anything so insane in all my life. Look at that. Apart from that last little bit there for some reason or other, which is a bit knotty. Look at that, look. Just that last little bit there. I mean, can you believe that? We've even got a lovely tarry residue here. Well, I don't really want to push my luck too much because we've already beaten projection A with 2mm a second. Do you think we should be able to get 3.2 or 3mm a second with our 0.5? Worth a shot, isn't it? Well, what can I say? Look at all that smoke coming out underneath. I mean, that is unbelievable, isn't it? But you're seeing it for yourself. This is no trick photography. So it only just made it through, but hang on. That's all it's got to do, because look, just a little. Well, you saw it first here. So if you want to test your machine, try it on a piece of 26mm English oak. That'll tell you whether or not you've got a good machine. We're going to go into the office shortly, and we're going to have a bit of a discussion and a bit of a look at some stuff under the microscope. But before we do that, what I'd like you to see is our cut face that we've just done. And square on the surface. Now, as I move that around, you should be able to see light underneath there. In fact, if I lift it up, you can see light under it. If I put it down, it's completely, absolutely square from both sides. How does that happen? Apart from perfect setup of the machine, everybody tells me we get angled faces because of the way in which the beam either converges or diverges depending on which argument you listen to. So I want you to make a note of that point, because that is one of the key things that I think we're going to be discussing when it comes to how does this machine actually produce a cut. Well, okay, what we've got here now is the some of those tracks that I burnt in to acrylic, and we're just going to take a look at one of them. This is typical because they all look very similar, but you might think that they're nice, clean, burnt tubes. It's difficult to see with such a high magnification. I've got two sorts of light on this microscope. I've got a halogen light, which I can adjust up and down, and as I adjust it down, so the camera is automatically correcting the exposure. If you take a look down here, you will see there is like a heat affected zone around the tube. And then you've got the tube itself, which has got reflections in it. And I've also got some LED side lights on here, which I can put onto the situation. And there we go. Now you can see the, if you like, the outside shape of the tube. So I can change these lights, the angle of the lights, to up and down. Let's try and leave them there at the moment, because that sort of gives the impression that we've got a bit of a tubular shape. We'll gradually work our way down the tube and take a look at the edge, the very edge of the tube itself. You'll see that it's slightly bright, and if we stop and look, we see almost as though it's got like air bubbles in it. And as we're getting further and further towards the bottom, you can actually almost see that they're air bubbles. The bore seems to be getting smaller, but in fact I don't think it is. All that's happening is we seem to be getting more bubbles that are creating. Now look at all those looking, as I said, look, we've got the heat affected zone here, which you can see, and then we've got all these little almost stress cracks that are going out into the heat affected zone. They're not part of the bore, but they're part of the, if you like, the shape that you will see when you observe this in natural light. So the shape that we see is this shape here, because now you can see that there isn't any heat affected zone. This all is effectively the heat affected zone. And then when we start moving back up, you'll gradually see that there is less and less of these stress cracks, and the heat affected zone is actually now out here. You look as though we've only got a very, very small bore down the centre there. Now I'm going to move right to the top, because right at the top there, if I bring it into focus correctly up, now you can see what I've done there. Look, I've got a 0.1 diameter copper wire that I've poked down inside the bore. Now although it appears to be shrinking, it can't be, because it's a 0.1 piece of copper, and it goes all the way down to the bottom, right down here. Look, there's the copper colour, and you can see where it stops here. So it's 4,000, it's more than 4/1000 of an inch all the way down, except this last little bit where it's jammed in just there. So that's a very, very thin hole that's being punched in there, 0.1. And then another one that was interesting. Now this is my compound lens. The thing about the compound lens is it's attempting to concentrate all the light at the surface. Unlike a cutting lens where we're trying to get the light down into the material, the lens has got to perform a completely different function. And it is doing so pretty well, because there is no parallel part to that beam, as you can see, just possibly, but because it's out of focus in the top of the material, it's very difficult to see exactly what's going on. But technically what should be happening is that the laser beam should be coming in at this angle, and as it comes in, it passes through its focus, and then it starts diverging. And as it starts diverging, look, you can see that it's actually scouring away the inside shape of the tube, getting bigger and bigger and bigger, and then it starts to get smaller again and stops. So it produces this teardrop shape purely because everything is focused at the surface. It's no longer a tubular shape. There's a clue here about what is happening when we play with lenses. How it is that we get from this to the other shape that we saw, which was a parallel tube way, way deep into the acrylic. How do we get these two different shapes from a lens? I'm going to be a little bit sneaky. I am not going to tell you in this session how lenses work. What we've had is lots of clues as to how the light is busy scouring away different shapes in acrylic. I've shown you some of the very interesting properties that lenses have and some of the tricks that they can perform. I say tricks, they are properties that the lens possesses. Think back to that piece of 26mm thick wood. It produced a perfectly parallel cut through 26mm, and it was square. It wasn't bent like this, which many people believe, you're going to get this effect on your cut because the light is diverging beneath the focal point. Well, it only happens like this in very special circumstances, and those special circumstances are when you are concentrating all the energy directly onto the surface, the focal point, the spot size. Now I'm starting to give away a little bit of a clue about how lenses do their cutting, but I'm not actually going to tell you today. We're going to go through my theory of how lenses work in conjunction with a laser beam to produce the effects that you have seen. This failure to find a suitable compound lens that matched my dreams has actually been a tremendous benefit to me, because it's uncovered some facts that I've been looking for a couple of years now, which completely explain how lenses work and how they cut all these fabulous parallel shapes. The kerf is always parallel. Deep holes that you've seen, they're parallel, but some of the holes are not, as I've demonstrated here. So what makes the difference between these non-parallel holes and the parallel holes? It can't be focal distance, because focal distance still concentrates all the energy at the surface. I'm going to wait about 2 weeks before I publish my results. I'm telling you now so that you don't get upset when I don't publish something in a week. If you understand how lenses work and how they cut deeply into material, doing some of the things that you've seen me doing today, demonstrating, please explain to me, because I don't want to be in a position where I say to you, look, here's how lenses work, and somebody says, well, I knew that all the way along. Now, if you're that clever, tell me now, because I absolutely know how lenses work. And on that challenging note, I'm going to say thank you very much for your time and patience today, and I'll see you in about 2 weeks' time with lots of answers from you and the real answer from me. See you in the next session. Bye now.